So in spectroscopy also we have firstly, if I'll talk about IR spectroscopy, because optical spectroscopy we have already seen, that's nothing but your absorbance versus wavelength. So that's a measure of the absorbance versus wavelength. So you will get a peak like this way. So this will tell you about the electronic transition has happened from one level to other level, that electronic states, and that will be comprising of certain energy. Say for example, if a molecule is having pi to pi star transitions, you know that in a molecule they are comprising of non-bonding orbitals, pi orbitals, pi star orbitals, sigma orbitals. So if I'm taking this pi and pi star, that is having certain energy, and that energy is relating to certain wavelength, frequency, or wavelength, whatever the way you want to say. When that energy happens, that absorption happens, you will see an absorption peak over here at that certain wavelength. That will call as an absorbance at that particular band. That is what we were seeing in the optical spectroscopy. Now, opposite of the absorbance, there is something called transmittance. That means if you have a sample, this we talked about in Beers-Lambert law. This is a material, and I am sending some I naught amount of energy. Some would be absorbed and some would be transmitted. So this I double dash is nothing but your transmitted amount of light, and that I dash is your absorbed amount. Right? So these are two different things. So that's why in case of optical spectroscopy or UV spectroscopy, you see the absorbance like this way. Whereas if I'll talk about the IR spectroscopy is nothing but when there is a change in dipole moment, transition between the vibrational states. So you know that in a molecule that exists as an electronic states, translational states, rotational energy states, and the vibrational states. You can go back and revise these basic concepts that we have read in graduation. So when we have this kind of system, say for example here, so these small lines that I'm making, these are my vibrational state, nu1, nu2, nu3, and nu4, and so on and so forth. So when there is a change in dipole moment, there happens a transition over there, and corresponding to that, we have a plot wave number, that is centimeter inverse, and transmittance percentage, and this will give you this kind of peak. Earlier, in case of the absorbance, we were having the peak like this. Now it's inverted. So you exactly get a wave number at what the transmittance is happening. For example, in case of this methanol, this is having negative, this is having positive. Dipole interactions are there. That is having permanent dipole moment. So normally, this OH will come in a region of 3400 centimeter inverse. So this peak corresponds to the presence of 3400 centimeter inverse, corresponds to the presence of OH moiety because of that permanent dipole moment over there. For example, different carbonyls would be lying from 1700 to 1800 centimeter inverse range, depending on whether acid is attached, aldehyde is there, ester is there, amide is there. So they will have a different range because they are having different dipole moment range, and corresponding to that, they will having an absorbance value different. Corresponding to that, transmittance would be different. So up to this point, is this clear? Both the optical spectroscopy and the IR spectroscopy?
Okay, ma'am.
Now, up till now, we were talking about the electronic states, rotational, vibrational states. Now, we will take our spectroscopy to another level, talking about the uh, energy states change among the nuclear level, nuclear magnetic states. So, these are defined as I, and corresponding to that, we have NMR spectroscopy. So the concept of NMR spectroscopy, it is defined as nuclear. This M stands for magnetic and R stands for resonance. So every single alphabet, that mutation has a meaning to it. So we'll take one by one. Earlier we were talking about electronic states, how the transitions between the pi star orbitals is happening. Now then for IR we talked about the vibrational states, and now we are talking about the nuclear magnetic states. So what happens? Nucleus and magnetism, how is it related? We need to understand that factor first. So firstly, the magnetism or the magnetic field, if I would say, that can only be generated if there is a spinning charge. Or I would say the movable charge species. What I'm trying to say, we know that we have two kinds of field. One is electric, one is magnetic. Electric field is related to stationary charge. When the charge is static, it is not moving. So that is giving you the electric. But the movable charges, which are having some movement, say for example, spinning or something like that, they will create a magnetic field. So this concept is first one. Now the second concept is nucleus is comprising of neutrons and protons. So they have spinning, they are moving, but they need to be charged, right? So protons are charged. They are charged particles, whereas the total charge of the neutrons becomes zero. That's why they are uncharged. But as a total, they are charged, movable. So they have spinning. The charge is there and they are spinning. So that is creating their own magnetic field. So nucleus creates its own magnetic field. Up till this point, it is clear? Is it clear?
Clear, ma'am. Nucleus creates its own magnetic field.
Yeah.
Okay, ma'am.
So similarly, if I have an electron, I will just say like that. We know that electron moves in an orbit and we know that it is having some spinning motion, right? It does not stay at a particular place. So it continues to move, right? So if it is moving in its own thing, it is having some spinning motion and it is having charge also, right? Similarly, if I'll talk about the nucleus is having protons which are positively charged and they are also moving like electron only. So that spinning motion with charge creates the magnetic field. Okay. Now I have one magnetic field and we know that how magnetic field interacts. If my hand is having some magnetic field over there, but until unless I provide a magnetic field, it will not start interacting. Say for example, in a basic way, you know that like dissolves like. So if I have a polar solvent, it will try to dissolve in a polar solvent. Because of the interactions of that polarity is there, they will interact either via hydrogen bonding or any other interactions. They like will dissolve in like. Similarly, non-polar would dissolve in non-polar. Similar in this particular case, the magnetic field, my particular ball or the pen is having a magnetic field, but until unless some similar kind of field is coming, it will not show any different behavior, right? So as soon as I have, say for example, it is having some random orientation. So both, it is moving like randomly. Some is going above. I will make you understand using a random rotation of the electrons. So suppose you consider the motion of electrons on these protons, the charge is randomly moving. They are having magnetic field, but they are randomly moving. There is not, because the net charge is cancelling out. Now, when we have put in presence of a magnetic field, they start orienting in particular direction. This is because they are interacting with the magnetic field. Similarly, when we have a nucleus, it is having protons and neutrons, and because of their continuous spinning and having a charge, they induce their own magnetic field, and that magnetic field interacts with the external magnetic field. So in NMR spectroscopy, we understand, okay, the two terminologies is clear. One is nuclear is clear, that by nuclear we are talking about, by nucleus we are taking, and what is magnetic. Now, what is resonance? So what happens? Normally, each nucleus you can consider any nucleus, every element is having nucleus. So I'm taking this proton, hydrogen, that H is there, right? So we call it as a proton in NMR spectroscopy. So this single H, because hydrogen would be H2, so this single H is having a nuclear magnetic state or spin value I equals to half. As we know that for quantum numbers, that spin state S equals to half plus half or minus half tells you about the spin of your electron, whether it is above or it is down. Similarly, in case of the nucleus, instead of S, it defines as a I equals to half. Is this clear? Do not get confused with the quantum numbers and this one. Just the way we have the spin states, spin quantum number, showing the direction of the spin of your electron up or down. Similarly, the nucleus is having its own spin value because it is spinning. So it would be either up or down or having another arrangement. That's why I'm talking about or giving it a symbol as I. Is this clear?
Clear, ma'am.
So now we understood that I equals to half is there, right? There could be two possibilities, the way we go from ml to plus ml to minus ml. So it is having two possibilities. Either it could be plus 1/2 or it could be minus 1/2. Why? Because if I have this state and this is like lying here, it is not doing anything. Now I'm applying a magnetic field. So along this magnetic field, one spin will try to go in this particular direction, and one would be having different energy. The one which is aligning with the V naught, that would be having down, and the other one which is aligning, which is opposite to the V naught, the external magnetic field, that would go above because of the higher energy. So firstly, we will understand the total magnetic energy that we are talking about, the nucleus, that is already having a negative charge. So when negative multiplies with the positive, it automatically gives you negative. More negative is the energy, more stability is there. So that has to be the ground state, right? That's why when I split it, this I equals to half in two states, that is splitting into two states, I put positive down and negative above. This means I applied my V naught, that is your external magnetic field. Earlier, there was no magnetic field. So these both states were degenerate. They were having same energy. So in absence of magnetic field. But in presence of magnetic field, so they were having interactions. One state goes aligned with the magnetic field. That's why it comes down. And because of the stability and lesser energy. Whereas the other one goes, if this is my external field, that goes down. So the spins were opposite. One is above, one is down. So that combination gives it a minus half value, right? So if I will take a case of nucleus, each nucleus is having different I value. Some are having same also. So that is not a problem. They are calculated from different model that I don't remember the name right now, but this calculation, we do not have to look for the calculation. These values are already known. So there is specific calculation from where we get to know about the I value for each and every nucleus. So I equals to 1, say for example, for deuterium. Deuterium is an isotope of hydrogen. So deuterium, which is having 2 mass unit compared to the one of the proton. So this I can split into +1, 0, -1 according to the ml range, right? So when I'm having I equals to 1, these 3 states are degenerate. They are not splitting in absence of the magnetic field. But as soon as magnetic field is applied, they would be having different interactions. The one which is I equals to 0, that does not interact with the magnetic field at all. That defines that net spinning or charge has become 0. So they are not interacting with the number of protons and the neutrons. They have become equal. So they are not having the orientation is just like that way, that they are cancelling each other's effect. That's why I equals to 0 remains as such, whereas -1 goes above, +1 comes down, right? So why is it so? This I equals to 1 you can consider if 2 arrows are there. So that becomes, this is half, half plus half is 1. So this is both the arrows, they are in direction of the V naught. In -1 case, both the arrows, they are down, and in 0 state, one is above, one is down, corresponding to the magnetic field. That's why I becomes 0. So these are nothing but these states which are up, they are called as alpha state, which are down, they are called as beta state. And this combination, I equals to 0, could be like alpha beta, or there could be like beta alpha. So in case of I equals to half, we got two systems, +1/2 -1/2, which is alpha and beta in presence of our magnetic field. So this is the energy difference, right? Now for I equals to 1, for second nucleus, there could be two same nucleus, that proton and proton, 2 protons with the I half, or one nuclei with the I equals to 1. So it goes like I is 0. These are called Mi values. And Mi equals to 0, Mi equals to -1, Mi equals to +1. This is a state where both are parallel, alpha, because each comprises of 1/2, so that becomes 1. This -1 is both are down, because -1/2 -1/2 gives you the -1. And here the case is 1 is above, 1 is down, or first one is down and above, other one is above. That is alpha beta, beta alpha. Here this is beta beta, and the down one is alpha alpha. Up to this point, is this clear? How do we define the nuclear spin states, and how they split when magnetic field is being given? How they interact?
Okay, ma'am, I understood.
So now we are talking about, so among the NMR, we were clear about N, the magnetic, we were clear. We were talking about the resonance. So we saw in this particular case, suppose I equals to half, we were having these two states, -1/2 +1/2. Now, if you'll see clearly, there is certain energy gap, right? So when there is energy gap, that is related to frequency, certain frequency. So what happens? Generally, all the states would prefer to be in a ground levels because of the stability. Ground state is the most stable state. So every system prefers to be stable. They do not want any randomness. They do not want any disturbance. So earlier, like all the states, if you'll see, everyone would be lying on the ground level only. But as soon as I am striking this one with certain energy, that h nu is energy. This nu is your frequency and h is the Boltzmann constant, which is a constant value. So what actually is changing, that's a frequency. So as soon as it strikes on these here, so they start going to upper state. That means now if 10 species would be down, and earlier case excited state was having 0. After that, they become 9, then it was 1, and further less 8, 2, and so on and so forth, right? So that means we are providing certain frequency or energy when it resonances with the energy gap. We know that energy is quantized. If I have to go from bar first floor to the second floor, I know there would be 10 stairs. So it can't be possible that there are now, I am decreasing the number of stairs, or I am increasing the number of stairs. It can't be like that. That is fixed amount. It's only that you're taking a bigger jump, but still energy required would be similar. The amount of energy that you have to give, or the time it is going to take, or something. I'm just taking a hypothetical situation. So going from one level to the other level, this energy is quantized. That should be having a fixed value. So as soon as, if suppose it is having X value and I'm striking it with X value, then only the molecules or something which are at the nuclei which are at the ground state, they will absorb that energy and then they will excite to the excited level, and that is called as a resonance. And because of this resonance only, we see an NMR peak. We see the spectrum because that is dependent on the electronic environment which is having around that particular nucleus, because nucleus is not surrounded alone. It is having some electron density always around it. So because of the changes in the electron around environment, it will affect your nucleus, and therefore depending on different nucleus in different electronic environment, they will be having different signals in the NMR spectroscopy. So up till this point, is this clear that basics? Our motive is not to understand more about the NMR spectroscopy. We're just making a base to understand the mass bar spectroscopy, like why these spectroscopies are important. So is that clear that how frequency and the resonance terms comes into picture? Until unless that resonance is with the total energy, that is the gap between the two states, it will not show any spectra. So is this clear?
Clear, ma'am.
Okay. Also, one more important factor is for any nuclei to be NMR active, it has to get the value greater than 0. It can't be 0. If I equals to 0, it will not interact with your magnetic field and it will not show you any spectra, because of number of neutrons and protons are equal. So they cancel out that effect. They do not induce any kind of magnetic field. So it has to be greater than 0. It can be half integer value. It can be integer value. Say, for example, 1/2, 3/2, or so on and so forth. Here, 1, 2, and so on and so forth. So all these would be nuclei active. And depending on different nuclei, you would be having different frequencies. We do consider that, okay, the quantized energy is there, but frequencies would be varying with respect to the nuclei. This you can go back and read in some any standard book of the NMR spectroscopy for any basic information. Now moving ahead, the main factor was that NMR, we talked about frequency, but what frequency it is using? It is using the radio frequencies. So these are having the least energy among all the electromagnetic radiation. So we have cosmic rays, we have gamma rays, we have X-rays, ultraviolet, then visible, then IR, then micro, and last is radio. So this trend, 1, 2, 3, 4, 5, 6, 7, and 8. Normally, cosmic rays, we don't talk about it. Normal spectroscopy is related to these ones, but I'm telling you the whole description. So this order is like energy is maximum here. These are having the maximum energy, followed by gamma, then X, and high amount of energy that goes more than 10 to the power 4 electron volt. So this much amount of energy they require. So you can see the radio energy is very less. So that's why nucleus can easily be, we can see the spectra very easily for any small change happening inside, or that electronic environment around the nucleus, if it is changing. we can give the radio frequencies, and corresponding to that, nucleus will behave differently. One more factor regarding this radio frequency. So generally we talk about in megahertz. So you might have heard about the NMR instrument using 400 megahertz, 500 megahertz. This is the frequency that we are using. So if proton, because it is 100% abundant, so there would be different isotopes which would be 100% abundant. So 1H is, because 1H is having number of protons as 1. So here the number of protons and neutrons are not same. That's why it can take up the 500 megahertz. So if I fix this frequency for proton or for proton nucleus, I need 500 megahertz frequency for that spectra to be seen. Now, 12 carbon C and 13 carbon C, there are many isotopes for this one. Here particularly, this is having certain 99 or 96%, and this is having only 0.1% abundance. So here if you'll see, the number of protons is 6. The number of neutrons is 6. So when we have both equal, that I value would be 0. So this can't be an NMR active nuclei, whereas only 13C6 is the NMR active among the 39 carbon isotopes. And this is very less abundant. Because of the less abundance, its values would be different. So this correspondingly requires only 126 megahertz. So the frequency range differentiates. They are not similar for each and every nuclei. That would be different for carbon, that would be different for fluorine, even if they are 100% abundant, because their magnetic moment, that is different for each and every nucleus. So we should not take more time in this particular spectroscopy. I hope you are understanding what I'm trying to say. We'll quickly shift to the next one. That is the electron resonance or EPR. So similarly, the way we saw that there is a transition between the nuclear spin states, similarly, there is a transition of the normal electronic states, and that is using your microwave radiations. So for example, here S equals to half, and it is going to S equals to minus half, S equals to minus half. Here the total energy is actually positive. So that's why negative into positive will give you negative energy, and that has to be down. Whereas in case of NMR, the negative value was above and positive value was down. So you do not get confused over here. So this also happens in presence of a magnetic field. And the radiation that is required for the transition to happen, that belongs to microwave region. So as you saw, microwave region or the radiation, they are having more energy compared to the radio. So they help in transition between the energy states of the electron. Okay. Now we are finally moving to our gamma rays, the last things that we have to talk about. Okay. So we understood about up till now we understood about optical spectroscopy, the UV thing, where absorbance versus wavelength was there. Then we saw IR, where we saw the transmittance versus wave number in centimeter inverse. It's in nanometer. Then we went ahead and saw the NMR, which will give you chemical shift, ppm, parts per million. So this you can go back and see. These kind of splitting would occur, doublet and triplet. Then we saw the EPR. This will also talked about the G values. 2.0023 for the electron, that's a gyromagnetic ratio, G factor. This will give you a signal like this one. And ultimately, so here we can see that UV is using UV light, IR is using IR radiation, NMR is using radio frequency, and ether is using microwave. Similarly, we have one highest radiation among them, that is gamma radiations. So gamma radiations is very, very high than the radio frequencies. You saw the pattern. So radio frequencies were giving NMR pattern. This gives you MOSFET pattern. So what happens normally? You saw that one nucleus can have a number of I states. It does not just stick to one state. So for example, one nucleus is having I equals to 1 by 2. It is also having I equals to 3 by 2. Right? So in presence of the B naught, this B naught I am saying, this is matching with a radio frequency. So for example, in case of the NMR. So this I by 2 will split into plus 1 by 2, minus 1 by 2. This 3 by 2 corresponding to the ML rules, it will go to plus 3 by 2, plus 1 by 2, minus 1 by 2, minus 3 by 2. Okay. Now, for the NMR to be active or the NMR spectra, the transitions will happen only between these two and among these. There won't be any transition from this state to this state. So, NMR is having the transition. I write here. So, in NMR, it uses the radio frequency, which is very important to remember. And the transition actually happens within the same nuclear spin state. Because of the less energy, the energy is so less that it can just stick to one state, and among one state there would be two different values. Up to that only it can have a transition. But if the other state is this much gap is there, that NMR, as I said, that it is quantized. So if I'm giving less energy, how am I supposed to go from ground floor to the 9th floor? So ground floor to the 9th floor, I need either lift, so can easily take me up to, so I'm providing an energy source. So that source is the gamma. If I have to go from ground to 9, that is only possible if I'm using the 9th floor. Otherwise, my energy would be exhausted at the 2nd floor itself, right? So since energy is quantized, we can't use the NMR or the radio frequencies to go from the ground floor to the highest excited level of the nuclear spin state. Whereas if in case of the MOS power, that is another spectroscopy and the second part of your course, that uses the gamma radiations, and that gamma radiations are having a transition between different I values or different nuclear spin states. So here, when the transition happens between these two, that occurs in the gamma region, and therefore it comes under MOSFET spectroscopy, which requires very, very huge amount of energy. That is not going to happen in case of the NMR systems. So up till this point, is this clear that what is the difference between all the spectroscopies, how we measure that, what is the difference between NMR and nucleus, this gamma MOSFET spectroscopy, how it is affecting, and later in next week, we will be starting talking about all the things regarding the MOSFET spectroscopy, why is it important, how do we measure it, how does it help in understanding many, many concepts in chemistry. So any question?
No question, ma'am.
Okay. So, okay, we have talked about all the spectroscopies and everything. Now we will take up the questions for this assignment. I'll still brief you what we have learned so far so that it would be easy for you to understand. So here, firstly, we talked about the application of the circular dichroism, and we were just having a brief concept about like what was circular dichroism, helical motion, the absorbance range would give you circular dichroism. And why are we talking about CD? Because our biological system, the basic unit of our body is DNA, RNA, and they are made up of proteins. Proteins are made up of amino acids, and amino acids are chiral. So how do we identify the structures of these kind of moieties? By using the CD spectroscopy. Because in CD spectroscopy, we have different bands for alpha, beta, and random core. So this was the first thing. Now later, we talked about the melting temperature of that particular protein structure. From going from one structure from alpha, beta to random coil or anything, it requires certain temperature. So higher the temperature, the maximum stability of one structure is there. If it is getting converted to or denatured to another structure easily, that means it is not very stable at that particular temperature, just like the case of the boiling point. Then we talked about the applications. So in general, when we are looking for some complexes, transition metal complexes or catalysts, so how do we get to know about the oxidation states in case when they are having chirality? So oxidation states and the change in their geometry or something, the distinctive peaks will not be appeared in normal absorbance spectroscopy. There we use series spectroscopy because the bands would be very distinctive. One would be appearing, and as soon as their oxidation state is changing, maybe that band would disappear. So that distinctive peaks we get it from the series spectroscopy. Similarly, the second example we saw that, okay, if we are talking about a catalyst which is used for the H2 production, but how do we get to know about their pH? And how are we confirming that it is coming from the chirality? So series spectroscopy clearly tells about the signature of the peaks, where we saw that at lower pH, it is giving the hydrogen production because that chirality is being induced from the carboxylate anions that are over there. And they are participating in giving that hydride or the H positive source to the metal system. And that is helping in H2 production. Later, we talked about here also we talked about the system. The guanine system. So we had a topic. Yeah. So here we took another example where we found that DNA is having a structural unit of this guanine quadruplex where 4 units are there and they're having different arrangements. We saw the guanine normal structure also where how the nitrogens have been named. And depending upon that, when we saw, they can arrange in different patterns. They could be parallel, they could be anti-parallel, they could be hybrid, depending on hydrogen bonding between different nitrogen centers. And based on that, we saw they're having different CD spectra. So parallel would be having 1 positive, 1 negative. Hybrid is having 2 positive and 1 negative. And anti-parallel is having bands in 2 positive and 1 negative, but the range is different. So 260, 240, and 295 are the 3 values that we need to be aware of. And the parallel can be observed easily because there are only 2. In case of the hybrid and anti-parallel, hybrid would be having 2 positive, 295 pay and 260 pay. And anti-parallel would be having 2 positives at 295 and 240, the highest and the minimum. So this we have to remember when we are citing that, okay, this quadruplex would be having this particular topology depending on the series spectral bands. And moving ahead, we took one example where we could see easily that how just looking at the spectra, we can see it is anti-parallel, it is parallel, or it is hybrid. Then moving ahead, we took the spectroscopy part into consideration, and spectroscopy generally gives us the intensity and the energy. Intensity is a quantitative thing. That means how many molecules or how many species are actually getting absorbed, transmitted, and participating in that particular phenomena. And energy being the qualitative form that among that it can measure your wavelength, wave number, at what particular value it is showing that number of molecules are getting absorbed or transmitted. Then we started with the IR spectroscopy. We talk about the optical spectroscopy, which is the UV region. It takes the UV wavelength, and we saw that absorbance coming, and absorbance versus wavelength is giving you the UV spectra. After that, IR spectroscopy, because of the vibrational changes that transition between the vibration levels, and because of the change in dipole moment, permanent change in dipole moment, we can see the specific value of your functional group because they are only the one which would be having permanent dipole moment. So that values would be fixed for each and every functional group that comes from the IR spectroscopy. Then we talked about the NMR, which is very important. So NMR is basically having nuclear magnetic resonance. Nuclear means this is involving nucleus. Nucleus, why? Because it is having protons and neutrons. So as a combination of both protons and neutrons, it is having spin also, it is having charge also.